Optical instruments, the eye. Here we are studying about the eye. This is also a optical instrument. There are different parts of the eye. We will discuss one by one. First one, cornea. It is outer curved transparent surface through which light enters into eye. This is the cornea. The outer part of the eye is called cornea. This is cornea. This is the outer part. Iris. It is a circular diaphragm having central hole. This hole is called pupil. The circular diaphragm has muscles and colored pigment. The color of the eye depends upon the color of these pigments. The function of iris is to control the amount of light entering the eye through the pupil. Pupil becomes small in bright light and it becomes wide in the dim light. Third, lens. The eye lens is convex lens and is made of transparent and flexible tissues. It is behind the pupil and held by the muscles called ciliary muscles. The lens focuses the image of object on the retina of the eye. For ciliary muscles. These muscles hold the eye lens in position. It controls the focal length of eye lens. When these muscles contract, the focal length of the eye lens increases. On the other hand, when they expand, the focal length decreases. Now retina. It acts as a screen to obtain the image of the object. It contains special cells in the shape of rods and cones. These cells convert light energy into optical signals, electrical signals. These cells convert light energy into electrical signals. These electrical signals are carried to the brain through optic nerves. The brain finally interprets the signal and hence we see the object as an image. Now near points. The nearest point from let us first see the structure of eye. Here is shown the structure of eye. The outer part is cornea, and then this is a aqueous humor, and this is the ciliary muscles which control the light coming in the lens. This part is called pupil, and this is the lens, and this is the retina where image is formed, and this contains the optic nerves, and this whole and this part is filled of vitreous humor, liquid. Now near points. The nearest point from an eye at which an object can be placed so that sharp image is formed on the retina is known as the nearest point of the eye. Near point of the eye. Near point of the eye. For a normal eye, it is 25 centimeter from eye. This distance is also known as least distance of distinct vision. Far points. The farthest point from an eye at which an object can be placed so that its sharp image is formed on the retina is known as far points of the eye. It is infinity for a normal eye. Range of vision. The distance between the near point and the far point of an eye is known as range of vision. For a normal adult eye, the range of vision is 25 centimeter to infinity. Now, power of accommodation. It is defined as the maximum variation in the power of the eye lens. Note the distance between eye lens and retina is about 2.5 centimeter average distance. So for near point, here for near point u equals to minus 25 centimeter and v equals to 2.5 cm, because distance between lens and retina is about 2.7 2.5 centimeter. Now using this formula 1 by v minus 1 by u equals to 1 by lens formula, we have 1 by 2.5 minus of minus 25 equals to 1 by f. This implies 1 by f equals to 1 by 25 plus 10 by 25 equals to 1 plus 10 divided by 25 equals to 11 by 25 centimeter. Hence, power of power near, for near point, power will be 100 by f in, then f is in centimeter, or 1 by f into 100, 11 by 25 into 100. Now 25 got 44, so we have 44t. So in case of near point, the power is 44d for eye lens. Now for far point, object is at infinity, so u equals to minus 50 and v equals to 2.5 cm. Again using lens formula 1 by v minus 1 by u equals to 1 by f. This gives 1 by f equals to 1 by 2.5 minus 1 by and u equal to 1 by 2.5. Hence p far equals to 100 by f into 1 by f into 100, 10 by 20, 25 into 100 equal to 40d. Because power is measured in diopter, so variation in the power 44 minus 40 equal to 40d, 4d. Thus for a normal eye, power accommodation is 4d. Now defect of vision. The first one is long sightedness or far-sightedness or hypermetropia. Long sightedness or far-sightedness or hypermetropia. In this defect, the defective eye can see far off objects clearly but cannot see the near objects clearly. Cause for this defect: increase in the focal length of eye lens, or second, decrease in the size of eyeball. This is here, this is shown the normal eye, this is the lens of eye, and this is the retina. Now this is the defected eye and this is also a defected eye. Here in this case the focal length has increased because lens has elongated, and so the near object, then this is a near object whose image is from the retina, but in this case because focal length has increased, so this object, near object, image is found behind the retina. Okay, then lens is elongated. Now in this case when eyeball is contracted, that is eyeball has decreased, that is this length has decreased. So here eyeball has decreased again because lens have same focal length, but retina has shifted it towards lens. So the image, near object image is found behind the retina. So in both cases image is found behind the retina. Now remedy. Now consider the near point of defective eye is at a distance d from eye lens. Consider the near point of the glass lens used for correction should make the image at distance d of the object placed at 25 centimeter. So we have 1 by f equals to 1 by v minus 1 by u. For correcting lens, v equals to minus d and u equals to minus 25 cm. So 1 by f equals to 1 by minus d minus 1 by minus 25 cm equals to 1 by minus 25 minus 1 by d minus 25 by 25. Hence f should be 25 d by d minus 25. We have to take d as a modulus value, or d is now as d is always greater than 25, so f is positive and hence the lens is convex. So this defect can be corrected by the use of convex lens. Now second, short sightedness or near sightedness or myopia. Short sightedness, near sightedness or myopia. In this defect, the defective eye can see clearly the nearby object but cannot see the far off objects clearly. Cause decrease in the focal length of the eye lens. Second, elongation in the size of eyeball. Elongation in the size of the eyeball. Here a normal eye is shown, and this is the defective eye, and this is also the defective eye. Here decrease in the focal length because curvature has increased, the lens curvature has increased, so focal length will be decreased. So ray coming from parallel ray, far object means the ray coming from the far object is parallel, so parallel ray focused on the focus. Now decrease focus, so the image is formed in front of retina, and in this case lens is same, but eyeball has increased, elongation of eyeball, that is distance between lens and retina has increased, but focal length is same, so the image will be formed in front of the retina. In this defect, the far point of eye shifts towards the eye. So correcting lens should make the image of the object placed at infinity at shifted far point. Consider the shifted far point is at a distance d from the eye. We have formula 1 by v minus 1 by u equals to 1 by u, lens formula. Now for correcting lens, v equals to minus d and u equals to minus infinity. So 1 by minus d minus 1 by minus infinity equals to 1 by f. Hence f equals to minus d. That is we take v equals to minus d, then f equals to minus d. Here also we put the value of absolute value of d. So in this case lens should be, because f is negative, so lens should be concave. So this defect can be corrected by using concave lens of appropriate focal length given by this formula. Now third is presbyopia. In this defect, I cannot see the near object as well as far off object clearly. This defect arises due to aging of a person. The ciliary muscles are weakened and the flexibility of the crystalline lens of the human eye decreases with the age of the person. As a result, human eye is unable to see the near as well as distant object clearly. This defect can be corrected by using bifocal lens. A bifocal lens consists of a concave lens which forms the upper surface of the bifocal lens, and 2. A convex lens which forms the lower surface of the bifocal lens. The upper surface of bifocal lens, that is the concave lens, enables the person to see a distant object clearly, and the lower surface of bifocal lens, that is convex lens, enables the person to see the near objects. Now, astigmatism. In this defect, I cannot see horizontal and vertical lines simultaneously. This is the case. Normal I can see vertical line and horizontal line clearly, but when astigmatism, I cannot see vertical line or horizontal line clearly. Cause this defect arises when the cornea of the eye has different curvatures in different direction in the horizontal and vertical plane. That is, the cornea is not spherical. Correction of astigmatism. It can be corrected by using cylindrical lens of desired axis and radius of curvature.